Welcome back to Grantage Deep Dive. Today we're tackling a pretty complex topic.
Yeah.
mRNA vaccines.
Definitely a fascinating one, though. It's one of those things you hear and you're like, wait a minute.
Yeah, how does that
How does that even work?
How does that work?
Once you get the basics, it's really cool.
And thankfully we've got Sarah here,
Yeah.
who's been doing a deep dive into all of the research
Yeah.
to help us understand this complicated,
Yeah.
crucial topic.
Glad to be here. It's exciting.
So before we get into the specifics of mRNA vaccines,
Okay.
you mentioned something to me earlier that I think would be a great starting point for our listeners about the different types of vaccines
Yeah, you're right.
that are out there.
It's kind of easy to just lump all vaccines into one category, but there are so many different approaches, and they all have like pros and cons. It's like saying all cars are the same just because they get you from point A to point B.
Right.
But under the hood,
There's all sorts of...
there's huge differences, yeah.
Yeah. So what are some of the different types of vaccines out there, and how do they differ?
Well, there's live attenuated vaccines,
Right.
and they use a weakened version of a virus. And then there are inactivated vaccines where the virus has been completely killed.
And then there are subunit vaccines that use only specific pieces of the virus
Right.
to trigger the immune response.
Exactly. And then
Okay.
we can't forget about toxoid vaccines. Those use a toxin that's produced by the bacteria to give you immunity.
Yeah.
And then there are viral vector vaccines. And those use like a harmless virus, but they're a delivery vehicle for genetic material from the target virus.
Oh, wow.
And then there are DNA vaccines. And those are similar to mRNA vaccines because they also use genetic material to trigger an immune response.
Oh, interesting.
But the key here is that mRNA vaccines are a whole different ballgame.
Okay.
They represent a completely new way of looking at and thinking about vaccination.
Okay. I'm intrigued.
Yeah.
So how are mRNA vaccines different from traditional ones?
So with traditional vaccines, you're injecting the actual virus,
Right.
either weakened or inactive.
Right.
But with mRNA vaccines, it's all about information.
Okay.
Like imagine you want to teach your cells how to defend themselves against a specific virus.
Okay.
So instead of showing them the entire virus, which could be dangerous,
Right.
you just give them the blueprint for one specific part,
Okay.
the viral protein.
So instead of the actual virus, it's like giving your cells instructions
Yeah,
to build a piece of it.
exactly. It's like you're giving your cells a recipe card
Oh, okay.
for that viral protein.
Gotcha. Like IKEA instructions, but for your immune system.
Perfect, yes.
So our cells,
That's a great analogy.
our cells are like tiny little IKEA furniture assemblers.
Yeah,
So they get these instructions, this mRNA blueprint,
okay.
and then what?
So our cells are amazing little factories, and they take the mRNA blueprint and they start churning out copies of the viral protein.
Okay.
But here's the thing. This protein isn't actually harmful on its own.
Okay.
It's just a fragment,
Gosh.
a tiny piece of the virus, and it's like a red flag that alerts our immune system.
Oh, so the immune system sees this foreign protein and goes, hold on a second,
Exactly.
this doesn't belong here.
Yes. It triggers this whole cascade of events.
Okay.
And the immune system starts to produce antibodies specifically designed to target that protein.
Oh, so it's like training your immune system,
Right.
but without the risk of exposing yourself to the actual virus.
Yeah, it's like target practice.
That's genius.
Right.
I got to admit, though,
Okay.
I'm still a little bit fuzzy on the whole mRNA versus DNA thing.
Yeah.
How does mRNA fit in with all of our genetics and heredity that we always hear about with DNA?
It's a common question. A lot of people get confused. So think of DNA as the master blueprint, okay?
Okay.
And it's stored in the cell's nucleus. It's like the permanent record of our genetic code.
Gotcha.
And then mRNA is like a temporary photocopy of a page of that blueprint.
Okay, so DNA is like a massive library of all of our genetic information.
Exactly.
And mRNA is like checking out a single book to reference.
That's a great way to put it.
Okay.
So mRNA carries a specific set of instructions from the DNA in the nucleus to the ribosomes,
Okay.
which are the protein-making factories in the cell.
Oh, so it's like a courier delivering a targeted message from the library to the factory floor.
Yes. And here's what's really important.
Okay.
Once that protein has been made,
Yeah.
the mRNA is rapidly degraded.
Oh, so it's like the book is returned to the library
Exactly.
after you've finished reading it.
Yeah.
This is a big deal because a lot of people are concerned that these vaccines are going to alter their DNA.
Yeah. Yeah.
But it can't happen with mRNA vaccines, right?
Exactly. The mRNA never even goes into the nucleus where the DNA is stored.
Okay.
So there's no chance that it's going to integrate with your genetic material or make any changes to your DNA.
That's reassuring to know.
Yeah.
So the message is delivered.
Uh-huh.
The immune system gets trained, and then the mRNA disappears.
Right.
Like a self-destructing message.
It is.
But there's still a mystery here.
Okay.
How does this fragile mRNA molecule survive the journey into our cells? It can't just be floating around in there.
Yeah, that's where the lipid nanoparticles come in. Think of them as tiny microscopic delivery trucks designed to protect and transport that mRNA.
Lipid nanoparticles, or LNPs.
Yeah, LNPs.
They seem like a crucial part of this process.
They really are.
Yeah.
They're basically these teeny tiny fat bubbles that encapsulate and shield the mRNA from degradation.
Okay.
It's like,
They're like
if you had a delicate glass figurine.
Bubble wrap.
Yes.
Yeah.
Exactly.
Okay.
Like if you were shipping it across the country, you wouldn't just toss it in a box unprotected.
Right.
That's what the LNPs do for the mRNA.
Okay.
They protect it from the enzymes that are trying to break it down.
So LNPs are like bubble wrap.
Yes. But these LNPs are also super clever. They're actually designed to fuse with our cell membranes and release the mRNA directly into the cytoplasm.
So it's like a key fitting into a lock
Yeah.
to deliver its payload.
Exactly.
You mentioned earlier that scientists are working on improving these delivery systems.
Yeah.
What are some of the exciting developments that are happening in that area?
Well, one area that's really interesting is using sucrose,
Sugar.
like regular table sugar.
In vaccines?
Yeah, as a cryoprotectant.
That sounds counterintuitive. What's the science behind that?
So when they add sucrose to the LNP formulation, it actually helps protect the mRNA from damage during freezing and thawing.
Oh, that's interesting.
And this is a really big deal because it's a game changer for storage and distribution, especially in areas that don't have reliable cold chains.
That could make these vaccines accessible
Yeah.
to so many more people
Exactly.
around the world.
Yeah.
Are there any other innovations coming down the pipeline in terms of LNPs?
There's a lot of research that's looking at different types of delivery vehicles, like polymer nanocarriers, which are tiny particles made from polymers.
Okay.
They're a potential alternative to LNPs. It's like they're constantly coming up with new ways to ship this important mRNA cargo to make sure that it arrives safely and efficiently.
So it's not just about delivering the message.
Right.
It's about
doing it well.
doing it in the best possible way.
Yeah, and all this innovation isn't just about improving the vaccines that we already have.
Yeah.
It's about expanding the possibilities of what this mRNA technology can do.
So we've been mainly focused on vaccines so far, but are there other applications for mRNA technology?
Absolutely. It's not just about fighting viruses. It's
Right.
about revolutionizing how we treat a range of diseases.
Okay, what are some of those other potential uses?
Well, let's start with cancer.
Okay.
Scientists are exploring the idea of using mRNA to train our immune system to recognize and attack cancer cells.
Oh, wow.
So basically giving our bodies personalized hit lists of cancer cells to get rid of.
So instead of chemotherapy or radiation, we could potentially use mRNA to harness the power of our own immune system to fight cancer.
Yeah, exactly.
That's incredible.
And it's not just cancer. mRNA could also be used for protein replacement therapy.
Okay.
And that would involve using mRNA to provide instructions to the body
Right.
to create proteins that are missing because of genetic disorders.
So it's like giving a missing piece of the puzzle to people with genetic diseases.
Yes.
That's amazing.
And we're really just getting started. There's also research being done using mRNA therapies for autoimmune diseases.
Wow.
And heart disease.
That's groundbreaking.
It is.
Sounds like mRNA technology has the potential to transform medicine as we know it.
Yeah.
I'm curious about the challenges, though.
Yeah.
What are some of the things that researchers are still facing when it comes to this technology?
Well, that's a great question because it's not all easy.
Right.
One of the biggest challenges is the stability of mRNA molecules.
We talked a little bit about that before.
Yeah.
With sucrose and cryoprotectants being used to protect the mRNA during freezing and thawing, it sounds like stability is an issue beyond just storage and transport.
Right. It's about making sure that that mRNA stays intact.
Right.
Long enough to do what it's supposed to do once it gets inside the cell.
Right.
And mRNA is very fragile.
Right.
It breaks down really easily.
So even if you have this great delivery system with the LNPs,
Right.
the mRNA still needs to survive long enough to deliver the message.
Yeah, it's like if you had a really important letter,
Yeah.
but it was written on tissue paper.
Okay.
You need to protect it somehow so it doesn't fall apart before it gets where it's going.
Yeah.
And that's why researchers are always trying to tweak the mRNA sequence.
Okay.
And adding modifications and exploring different ways of delivering it.
Right.
They want to maximize the stability, and they're getting very good at outsmarting those enzymes that want to break down the mRNA.
It's like a constant arms race between scientists and these enzymes.
It is, yeah.
So stability is one challenge.
Yeah.
What are some other hurdles that are out there?
Another big one is targeting. So we talked about the LNPs and how they deliver the mRNA.
Right.
But we need to make sure that it gets to the right cells.
Right. It's not just about getting into A and Y cell.
Exactly.
It's about getting into the specific cells that are involved in the immune response.
Yeah, it's like delivering a pizza to the right house.
Okay, yeah.
You don't want it to go to the wrong place.
You want to go into the wrong house.
Exactly.
Yeah.
And just like a pizza delivery driver needs an address, researchers are finding ways to modify the LNPs with targeting molecules that can guide them to the right cell types.
So it's like putting an address label on the delivery truck.
Exactly.
So it goes to the right place.
Yeah.
I imagine that adds another layer of complexity.
It does.
To the whole process.
It does.
Are there any other challenges?
Well, another one is managing the immune reactions.
Wait, but isn't the point of a vaccine to trigger an immune response?
It is.
Okay.
But we want that to be controlled.
Right.
We want to target it.
Okay.
Sometimes your body can overreact to the mRNA.
Right.
And that can cause inflammation and other side effects.
So it's not just about getting the immune system fired up.
Right.
It's about making sure it's focused on the right thing.
Exactly.
And not causing other problems.
Yeah, it's like training a guard dog.
Okay.
You know, you want it to be protective, but you don't want it to bite everyone that comes to the door.
Right.
And that's where those nucleoside modifications that we talked about come in.
Okay.
By tweaking the mRNA.
Right.
Scientists can actually tone down those immune reactions.
So they can fine-tune it?
Yes.
To make it as effective as possible, but minimize any sort of side effects.
Exactly.
Are there any other challenges you want to mention?
There's also the fact that scientists are always looking at different ways to administer the vaccines.
Okay.
Right now, we mostly use injections into the muscle, but they're looking at other options like intranasal.
Through the nose?
Yeah, through the nose, or even orally, like through the mouth.
Wow. That would be...
It would be great.
Amazing.
Imagine getting a vaccine with a nasal spray or taking a pill.
Right.
But those methods have their own challenges.
Okay.
Because the nose and the digestive system are very different from muscle tissue.
Right.
There are enzymes and other things that make it hard to deliver the mRNA.
So it goes back to that stability issue.
It does. You need that mRNA to be strong so it can survive those harsh environments.
So it's like designing a spaceship that can travel to different planets.
Yeah.
That have different atmospheres and different gravity.
Exactly.
And that mRNA has to adapt to its surroundings.
It does.
That's fascinating.
It is.
Well, Sarah, this has been a fantastic deep dive into the world of mRNA.
It has.
Thank you so much for being here and sharing your expertise with us.
It was my pleasure. I always enjoy talking about this stuff.
And to our listeners, thank you for joining us on this incredible journey. We hope you've learned a lot and you're as excited as we are about the potential of mRNA technology.
Remember, stay curious and stay informed.
That's it for this episode of Granogen Deep Dive. We'll see you next time.